Let's look at an example of a light bulb. Everybody turns on a light bulb. Let's just say we've got 110 volts coming out of the wall. We've got a 100-watt light bulb. What's the resistance of the light bulb? Plug in your numbers there. It's 121 ohms. So your light bulb, if it's 100 watts, has a resistance to the current flow of 121 ohms. Let's get back to what actually happens inside of things. There's electronic components. I'm sure everybody's at least seen a picture of a piece of electronics opened and you see all of these pieces on a circuit board soldered in. I know personally I have many times because my board used to break down every other week and I'd have to pull out the circuit boards and figure out what went wrong. And you'd touch around and go, what's hot? And then you'd smell it and go, what burned up? And then you go, oh, it's that resistor. I see, it's all burned. I'll replace that. Plug it back in and it works again. In general, there's a couple different kinds of components on that circuit board. Active components are components like batteries and other power sources, amplifiers, transistors, tubes. They provide energy and require energy. So what transistors do and what tubes do, and what they basically do is they take a power source, they manipulate it the way you want it to be manipulated, and then spit out more power in a different kind of fashion. But they all require energy to work. That's why you got to plug in your appliance to make it work. It needs power to work, and then inside the piece of gear it manipulates the electron flow to get exactly what you want out of the piece of gear, whether it's a television or a tape recorder or an iPhone or a computer. Now your computer, on the other hand, and your iPhone, they have batteries inside. And so when you run low on your battery, you go to the wall, you charge it up, right? Coming out of the wall is AC. It's 110 volts, 60 cycles, alternating current. It gets to that little white wart there that you're seeing down on the floor there, and that converts it to DC. And then the cable that comes up into your computer is direct current, and it actually charges the battery up, refills it, so to speak, like a gas tank filling up, and then you can go for another charge until it drains down again. So we use the conversion between AC and DC all the time. We use AC primarily for distributing power from places to places because it's safer than DC. But inside the pieces of gear, most pieces of gear operate on DC, except, of course, things like fan. A fan is an AC unit. It uses AC, doesn't convert to DC at all. Your refrigerator uses AC for the compressor in the refrigerator. Your vacuum uses AC to run it. But almost everything else I can think of converts it from AC into DC. So you plug in your TV, goes into a circuit that takes the AC power source from the wall, converts it into DC, and then utilizes that to run your TV or whatever other kind of pieces of gear, whether it's a stereo amp or whatever, runs on DC. Inside the unit, on the outside, it's got an AC plug to get the power. We talked about active components like transistors and tubes. Let's talk about passive components. Passive components, they use energy in a circuit. They don't give back energy. And resistors, resisting the flow of current, is a passive component. Capacitors, inductors, transformers. Okay, so we've got electrical symbols. Symbols for each kind of component. There's a resistor is the squiggly line, so it means current has trouble flowing through it quickly. Variable resistors, like this one over here, with an arrow, meaning that you can turn it up or down. This is a battery symbol of a battery. Speaker, capacitor is an energy storage device. Transistors, LEDs, light-emitting diodes. That's what actually is inside all of this here. It's a way to manipulate electrons, manipulate charge. Capacitors are not very difficult to understand, and resistors aren't, but they're the basic components of what goes on inside your computer. Of course, then there's microprocessors and transistors. That's what goes on with manipulating electrons so that once the sound is transduced into the electrical domain, then we can manipulate it using these components and create something a little different and then send it back into the acoustic domain through a speaker. On your guitar, right, you've got a tone control. You roll off the high frequencies by making it duller or brighter. It's a passive device with capacitor and resistor. You change the resistance value by turning the knob, and as you change it, more high frequencies go away. When you think that you're adding more bass, you're actually just taking away top. And when you open it all the way, then you get the most high frequencies. And that is in every passive Strat. Any passive guitar has that as a tone control. The same thing applies for a wah pedal, like what Hendrix used to use, wah, wah, wah kind of sound. With his foot, he would move the resistance, and it would change the resistance of the signal going through, and it creates that sound. But those are two really simple ways that just a resistor and a capacitor change what you end up hearing. But it gets more complicated than that because a lot of the electronic devices get power, and so they have active filters. This is all passive at the moment, meaning that there's no real amplifier involved. What I'm trying to show you is that with a capacitor and a resistor, you can actually manipulate sound, or the electrical signal that'll eventually become sound when it hits the speaker again. And that's actually what you do when you turn your knob on your guitar or your tone control on your stereo or whatever. You're actually manipulating those electrons to pass in different ways.